Okay, well, I'm very honored to be here. First, I'd like to say it's been a pleasure the last a number of years to have a chance to work with Alex. I've learned a lot, and most I've learned quite often what I don't know, that I should know. So today, I'm going to give a presentation on, instead of a big overview, focus on just a few processes. Could I borrow your pointer? Sorry. Thank you. Okay, that should work. Just quick. That one. Okay, thank you. Okay. All right, so I'm going to focus on the formation and destruction of H-, which is actually a little project that Alex proposed, I'm embarrassed to say, 10 years ago we started looking at, and I've not really finished it, and I thought that I would discuss this as a motivation so I can get this done. Another benefit of working with Alex, as he has so many collaborators and former students, that you end up having an opportunity to collaborate with many of them, very wonderful people. And from this particular project, there's a number of them who are involved, and everyone's here in this little project I'm going to discuss, except for the first one, which is my student, Shinya Miyake, who's done some of the calculations I'm going to show. Okay, so here's just an overview of the topics I'm going to discuss. We're going to focus on H- and something that Yvain already mentioned, radiative feedback. And then I'll discuss a little bit about H- atomic physics, which I'm sure many people here know about. Okay, so the focus or the context for my talk is the early universe, but I'm not going to really talk about early universe chemistry, but the a few of the processes that are really important in early universe chemistry. And you've heard a little bit about this from our first speaker, Yvain. And it turns out that in the early universe, there are no metals, and we're interested in the formation of molecular hydrogen. It was proposed in 1961, so by McDowell, that you can make H2 and a zero milliliter gas through this sequence of reactions, radiative attachment to make H-, and then followed by associated detachment to make H2. And it was also later pointed out by Peoples and Dickey that would be important in the early universe. And so this turns out to be the dominant way to make H2 in the recombination era. So after hydrogen has recombined, but before we make the first stars. Okay, so that's redshifts of less than 100 to about 10 or 20 or so. And it also turns out to be very important in the formation of the very first stars, so-called population 3 stars, until the density gets to about 10 to the 8th, and then 3-body processes become important. In general, this is not very important in contemporary star formation, but there's been a few studies that looked at, well, where would it be important? And Simon Glover did a little study to see where this sequence of reactions is the dominant way to make H2. And of course, you expect it to be in low metallicity gas, and he just parameterized where it would be related to the dust to gas ratio of the Milky Way. So some small metallicity regions, these two processes could dominate the way H2 is made. Of course, when the metallicity is high, it's made off of grain surfaces. Okay, let's see. Okay. So H- is suppressed at the really early redshifts because of photodetachment due to the background radiation field, which we've discussed earlier. And where the temperature of the radiation field is very high, photodetachment is very efficient. But as soon as the universe starts to cool, the radiation temperature drops, and then this process becomes inefficient, this process of photodetachment of H-. So that's the main destruction mechanism for H-, except for the associated detachment. Interesting, it also turns out that a radiation field could enhance the formation of H- through a process that Alex and I looked at 10 years ago, stimulated radiative attachment. And we considered just a black body radiation field. And I'll show a little bit later, this also could enhance the formation of H-. And in the early universe, just at recombination, a lot of photons are produced by recombination, and the cosmologists call the distortion photons, so additional photons beyond the black body radiation field, which also could play some role in the association of photodetachment of H minus. Okay, well, I should step back a little bit. For H minus, it's easily destroyed by photodetachment. But in this era, there's really no process that destroys H2 very efficiently. Okay, so H2 is free to form as much as possible. It's only limited by the low density of the gas early universe until the first stars are formed, so-called population 3 stars or other type objects that are formed. And they're thought to be very massive, and so they produce a lot of far ultraviolet radiation. And once this radiation field is produced from these stars, you can imagine when the first star is formed, it's formed in a universe which is completely atomic hydrogen, so a neutral environment. Then you have the first star form, emitting a lot of UV radiation, so it creates a Stromgren sphere, an H2 region, okay, which slowly expands out. Kind of like, and you have various population 3 stars formed in different places, making like Swiss cheese. Okay, so these energetic far UV photons can ionize the hydrogen around the star above the Lyman limit, but then below the Lyman limit, they could also dissociate any H2 that's around, the so-called Solomon process, which Elaine mentioned in her talk. And so cosmologists who were interested in the formation of the first stars began looking at this, and the first bullet here has the effect of producing more electrons and therefore ionizing the gas and driving chemistry. So if we're interested in, after the first star is formed, what happens to the region nearby? Is another star going to form? Okay, that region nearby experiences the photons from the first star, and the one effect that could happen is a so-called positive feedback effect. We produce more electrons, therefore drive the chemistry, making more H minus through this H minus mechanism for making H2. And that was investigated 10 years ago by Zoltan Hyman, Avi Loeb, and so-called positive feedback effect. The other thing, of course, that could happen is the H2 is directly associated through the Lyman-Warner bands. And that year later, they came out with a paper, this is a negative feedback. Feedback meaning these photons now will slow down star formation by removing H2. Okay, and here's a similar plot that we saw earlier, just describing this Lyman-Warner band process. We're down here in the ground state of H2, far UV photons excite itself to the B and C state, and then they can decay back down to the ground state. But it turns out that about 10% or so go to the associative continuum of the ground state. Okay? And this process, as they mentioned, was the rates were calculated by Stevens and Alex a few years ago, and then more recently by Avgrel has updated some of these rates. Right? So this is a mechanism now for destroying H2 in the early universe, or regions that are near some sort of population 3 star. Okay, so we have a way to make H2, associated detachment, and then a way to destroy it by Lyman-Warner photodissociation. And so we can estimate what the abundance of H2 is, okay, by just setting them equal. At the top we have the formation rate of associated detachment divided by the photodestruction rate due to Lyman-Warner bands. Okay, well, why is H2 so important? As they mentioned, in the early universe, it's really the only coolant that's available. Okay? And it's very important to cool the primordial gas during the collapse of some high-density region to develop to make a star. You need to radiate away the gravitational energy. Okay, so formation of H2 provides for this cooling, and then the cooling ends up controlling the star formation efficiency of these early objects. Okay, so if the H2 that's in some nearby region near a population 3 star is dissociated, then we reduce the cooling efficiency, and then we're going to therefore reduce the star formation efficiency of the next generation of nearby generation of stars. And it also has a possible consequence of what happens in the next stage of the universe when all these population 3 stars sweep through the universe ionizing all atomic hydrogen, the so-called reionization era. That could be delayed if the star formation rate is suppressed. Okay, so that's the reason why we're interested in H2. And so a lot of cosmologists have started to model these Lyman-Warner bands in the formation of primordial gas near a population 3 star. And mostly they've interested in just the photons between 11.2 and 13.6 eV, and looking at what the effects are on this star formation efficiency. Well, when these stars are formed, they also produce energies, photon energies much less than that, which could photodetach H-. And the cosmologists really had not considered that before. And it was just pointed out just last year by Chozhoi, Kulin, and Shapiro that H- photodetachment should also be considered in these models. And so they said, okay, if we don't have much H-, we can't make H2. And so they wrote down a suppression factor for the formation of H2 just due to the H- photodetachment. So it's H- photodetachment rate, beta, divided by the formation rate of H2 plus 1. And they performed some empirical modeling studies of various primordial gas environments, and they found that this suppression factor could be as much as 1,000. Okay. And this is if you consider the first star is formed, it produces UV radiation, the UV radiation goes out into the gas. Of course, all of the Lyman limit photons are removed completely right away through photonization of atomic hydrogen. And so then you look at all the hydrogen recombination lines that occur, and they cascade down, and they considered all the photons that are produced less than the Lyman alpha, 10.25 eV, and they found that this suppression factor was very large. And then they considered the next stage, okay, population 3 stars also emit radiation just due to black body radiation, which gets out of the halo that surrounds the H2, the population 3 star, all photons less than 13.6. And if you consider a various range of masses for those population 3 stars, at the very more massive stars, 100 to 1,000 solar masses, it enhances this suppression factor by 10%. If you considered actually stars that are maybe 10 solar masses, it enhances it by another factor of 10. And so a suppression rate could be very large on the formation of H2, just considering this photodetachment. And then they looked at another type of object which is believed to be formed early on, a mini quasar. And mini quasars have a different type of radiation distribution, usually adopt a power law spectrum. And if you consider the mini quasars, the suppression factor is about 5,000. Okay. So, getting to the real point of my talk after this introduction, what Chozhoi did was to consider the photodetachment cross-section, but just the smooth continuum part in their calculations. As I show here, which was attained 79 by Wishart. Okay, so it's the cross-section versus the photon energy. However, all those atomic physicists know that the stories are more complicated. Right? There are a large number of doubly excited states, and the first series of those goes up to the H=2 threshold, and they produce very strong resonances. So there's a shape resonance and a Feshbach resonance here at about 11 eV. And they neglected this. So after seeing this paper, so what effect does this resonance have on the photodetachment rate? How strong is that? And in fact, I looked through the literature, particularly in some of the cosmology models of the H2 feedback, and they have all neglected this resonance. They all consider just the photodetachment, the smooth photodetachment cross-section. Okay, so this proposed a very simple idea. How is the photodetachment rate influenced by including the resonance? And so then what I'm going to show today is just the ratio of the photodetachment rate with the resonance and the background without the resonance. Okay? And so this is the photodetachment rate with the resonance and divided by just due to the background cross-section. And forgetting that factor of 1 in suppression factor, it's the ratio of with the resonance and without, and I'll call this the suppression factor for the resonance, just the contribution from the resonance. And I'm going to consider a couple of radiation fields, and the first one is a black body radiation from these population 3 stars. Okay, consider ranges from 10 to 1,000 solar masses, which are effective temperatures from 10,000 to 150,000 Kelvin or so. And we also cut off the radiation field above 13.6 eV. And we find this, so applied here, suppression factor is a function of effective temperature, and here is 1, so no effect. And we find that the effect gets up to about 9% for the most massive stars. And may be a little bit larger over here for the very small stars. So kind of a small effect for black body radiation, the most 10% if you include the resonance. Okay. And you can kind of understand this little minimum here by looking at the black body spectra. So I plotted here again the cross sections, and now here I've overlaid spectra for black bodies at 10,000, 25,000, and 50,000 Kelvin. So the high temperatures really access the resonance, while the lower temperatures go down here to look at the broad peak near threshold. And in the middle, at 25,000, we kind of fall between those two features. Okay. But then we looked at another type of radiation field, which is used a lot in cosmology, that is the power law, and it could could be applicable to a number of type of objects: quasars, active galactic nuclei, massive black holes, just an intergalactic medium, or these mini quasars. And here the radiation field is just given by the frequency of the photons divided by the frequency at 13.6 eV of hydrogen to this power law minus alpha. And so we've done the same calculation, calculated the effect due to the resonance, and here is a function of the power law index from 0.1 to 5. Okay, so at about 0.7, which is typically used in cosmology modeling, we find that actually the rate is enhanced by a factor of 2, just due to the resonance. And if we go up to a little bit higher power law to 1.7, which is relevant for many quasars, it's enhanced by a factor of 3. Okay. And of course, we can understand how that enhancement works by plotting here the cross-section versus the radiation field. So I've shown for different power laws from 0.1 up to 5. Okay. And you can see that there's a big jump in the radiation field near where the resonance is. And so adding up all of these contributions, the Chernay paper found that the enhancement was 5,000 for the mini quasars if you neglect the resonance. If you add in the resonance, another factor of 3, so the total suppression factor for that particular case is about 15,000. So the amount of H minus would be reduced by that amount, and so forth, and presumably the same amount of H2 reduced by that amount, which would suppress the cooling in such objects. Okay. Well, then we looked at a little bit more complicated radiation field, okay, which is the radiation field that's produced as the photons leave the population 3 stars and propagate through the surrounding atomic hydrogen. Okay. And a number of cosmologists have tried to model this, but mostly they were interested in the photons near the Lambda-Warner bands. And so we had to put together a bunch of different spectra that try to come up with the photon field over the whole interesting photon energies. And so we combined the number of spectra calculated by these various groups, and then we added on below 6 eV just the power law spectrum. And we get this interesting looking spectrum here, which is also often called the sawtooth spectrum. Okay. And so this is the power law here, and over here we have all these absorption features due to atomic hydrogen. And so how to understand this, We're interested in some region here, all around it. Population 3 stars are going off, population 3 stars are forming, and their radiation is propagating across the universe. Cosmological distance, okay, most of the Lyman alpha or Lyman beta is absorbed near the star, okay, but then the remaining photons propagate to the source we're interested in. And so you have this kind of sawtooth pattern that's formed. And what immediately stuck out to me when I thought about this is there's a feature here that's due to Lyman beta, and then over here there's a feature here due to Lyman alpha. And of course, this resonance falls right between those two features. Of course, it should, right, because it's shifted by 0.75 eV. And so there's a window for this resonance could possibly play an important role in the photon detachment if you have this kind of radiation field. And just to emphasize that, here's sure another plot, how neatly it fits in this window. So there's be a lot of photons in here near the resonance. Okay, so we did a similar calculation. It turns out we actually find a similar kind of suppression factor for that more complicated radiation field. Factor of 2 or 3, depending on the power law. Okay, so in summary, considering this resonance, which the cosmologists left out, would increase the suppression of H2 by factors of 2 or 3 or so, depending on the model you adopt. Okay. Well, so briefly, I'm going to now discuss a little bit about the atomic physics. I did mention where the cross-section comes from. Of course, many people have calculated the H- photon detachment cross-section for many years. And when we first started this project, I had worked with Hussein to provide some of the cross-sections, so he did some arm matrix calculations, and Brendan has done some other calculations. And we also combined those cross-sections calculations with measurements and make sure we go to the correct limits near the threshold and at high energy, and to get a cross-section over the whole photon energy range. Well, once we have the cross-section, we also test how good is the cross-section by calculating oscillator strength sum rules. And in fact, this was done for H- by Alex and Ewart back in 1962. So we're just extending what they did there with more updated cross-sections. And here's a little table. Don't want to spend too much on the time of table, which gives the sum rules from k equals 2 to minus 3. K equals minus 2 is proportional to the dipole posability. Okay. And there's a whole bunch of range of values which have been calculated over the years from various people. And we adopted what we thought was the best calculations shown here on the right, so on the left, of each of these sum rules. And then we just took the integral of our cross-section times the moment of the photon energy and to see how well we did. You can see we do pretty well with the given cross-section for negative powers of k, but as we go up to k equals 0, 1, and 2, we're not doing quite as well. Okay. And part of that is these are at the positive k, that probes mostly the high energy part of the cross-section. And so also then added in the double detachment. That helps a little bit, but there's still something missing in our high energy part of the cross-section. But what we're interested in for the cosmology is really the lower energy, less than 13.6 eV. So in that region, our cross-section satisfies pretty well the sum rules. Okay. Well, as another side, once you have the photon detachment cross-section, by detail balance, it's simple to get radiative attachment. And in fact, as far as I can find, the first calculation that was done for that was done by Alex and Kingston. Okay. And they gave a radiative attachment rate coefficient. And it's been in the literature for a while, but then I noticed in 1998 or so, the rate that was in the UMIST astrochemistry database was wrong. It came from some other source. And about that same time, Alex and I recalculated it. And since then, the UMIST astrochemistry's website has been updated. And just to show Alex's previous calculation from 62, shown here in green, our newer calculation in 98, so his previous calculation still holds up. Okay? And this blue curve is the one that was in UMIST until a few years ago. Okay? You can see it's off by almost a factor of 10. Okay. But H minus is not too important in the interstellar clouds. So maybe people didn't notice it. Okay. And then I mentioned in the beginning we could also enhance the formation of H minus by considering a radiation field. And here we did some calculations for just black body radiation field. And the temperature has to be pretty high before there's an effect. So the red curve is 0, no field. And then the green curve is 5,000 Kelvin, 1020, up to 50,000 Kelvin. So there's not much of enhancement until we get to 5,000 Kelvin or so. But it could be enhanced by maybe a factor of 10 if we get over 50,000 Kelvin for a black body radiation field. Okay. Right. So in summary, I've discussed these few little processes related to H minus, which I've worked on recently with Alex. And we can see that they're important in the early universe. It's the main H minus is the main intermediary to make H2, but it could also be suppressed due to photodissociation, photodetachment, which also then suppresses the amount of H2 that can be formed. And try to show that some preliminary calculations that if you are careful about the atomic physics, you include these resonances, you can further suppress the amount of H2 that's formed. Okay? And if you do that, then this may affect the primordial star formation rate. It's after the very first stars are formed. Okay. Well, these calculations that I showed and what other people have looked at they've used very simple models. What needs to be done today is very sophisticated cosmological simulations where you can track the photons, radiative transfer through the hydrogen gas, and all the population 3 stars. People are just thinking about how to do that, in particular to be able to calculate what does the radiation field actually look like, this kind of sawtooth spectrum. Those are all models. Okay. So the next step of what we're doing now is we're trying to just improve the H minus photodetachment cross-section by converging them to the sum rules as best as possible. And then we could calculate even better, more accurate rates for rate of attachment and photodetachment. And that's all. Thank you.
Other questions? Please, John.
Yes, you looked into the effect of the resonances on the photodetachment, but did you also look at the effect of the resonances on the inverse process of radiative attachment? Because if the collision energy is large enough for the electron to excite n equals 2 in hydrogen,
right,
there should be some effect on the attachment rate too.
Right. Of course, it's about 11 eV, so it's 100,000 Kelvin. And H minus forming at that temperature is probably not much interest. But we could, and when we did this calculation, we didn't have the resonance end. But yeah, that's what we will do that next, but it would be at a much higher temperature.
Or you could start with an n equals 2 hydrogen.
That's true, you're right. Right. Yes, that's right.
Phil, can you comment? You showed very nicely how the formation rate is suppressed, but can you also, what is really the impact on the H2 abundance then that you get? Because obviously the H plus route still goes. So how much does the overall H2 abundance decrease? Sort of
how much is the H2 abundance decreased?
Yeah.
Well, let's see. Let's see back in here. Well, in this equation here, which gives the equilibrium abundance of H2, just the N H minus would be divided by that factor of F.
Right, but also H plus rates that still works.
Well, you're right.
So what is the equivalent to 10 to minus 6?
Right. So that's a very good point. Once the H minus process gets suppressed, then H plus would come in to be important.
Right.
Right. And yeah, so we didn't consider that part, but that's a very good point. Yeah.
I'd like to ask just on the question of excitation of the neutral hydrogen and then having radiative association of excited hydrogen, whether that sort of replaces the H minus as a
Okay.
forming.
Right, so like Hn equals 2 plus H goes to H2.
Right.
Right. That's a good point. In the early universe, there's not much of that, right, because the temperatures are too low. When the UV photons come along after the population of 3 stars, they could be promoted to that. And yes, maybe it could be a process that should be considered and could also take over from the H minus mechanism to make H2. You're right.
Are there other questions? Well, then we will see you next.
Thank you.